Hi gang, welcome back. It's another week of this stuff. So, way back in September, we figured out that there was a way to time how long it took for something to fall a certain distance. In fact, we had a nice neat formula that we simplified down for the special case of starting from rest. And it looked like this. T equals the square root of 2y over g. And so if I wanted to know how much time it took for this little magnet to fall through that copper pipe, all we need to know is the length of that copper pipe, and we could find out how long it takes to fall. So if this is roughly 4 feet of copper pipe, or 1.2 meters, then we can calculate this. We just plug in T equals the square root of 2 times 1.2 over g, and we'll get something that is close to half a second. Things like 0.49 seconds. And so we could drop this little magnet through that copper pipe and we could time how long it takes. And so what I'm going to do is I'm going to drop it one time outside of the copper pipe, one time inside of the copper pipe, and we'll see if there's any difference. 3, 2, 1. Three, two, one. So hopefully we can all agree that there is a very big difference between dropping the magnet outside of the pipe versus inside the pipe. But here's the thing, copper is not magnetic. So to figure out what the heck's going on, we're gonna have to rewind a bit. Click on the face of Nikola Tesla here. We can begin with our notes on magnetic fields. And so we've all seen magnetism. Magnets in our everyday lives. You know, the refrigerator magnets are these horseshoe magnets that you have, and this is a technology that's been around for thousands and thousands of years. There were rocks that were in this place called magnesia, and they did this weird thing, and because these weird rocks came from magnesia, those weird rocks were called magnets, and we were able to do a lot of things with them up to that point before we really knew anything about them. So just to get rid of the vocabulary that I'm sure everybody's aware of, magnets have two ends. They're called poles. You've got a north pole and a south pole. And a lot of people think of them sort of like the static electricity stuff that we talked about because they do similar things. North pole and north pole together are going to repel. South pole and south pole together are going to repel. But a north and a south pole, if you bring those together, they're going to attract. That's sort of like your positive negative charges with electrostatics, but it's not the same thing. And we got to make sure that we don't confuse the two. The most obvious example would be you take the balloon, you rub it on your hair, it'll stick to the wall, but it's not going to pick up some kind of magnet. There are two different processes that are occurring. Another major difference between electrostatics and magnetism is that if you were to take something that is charged, that has some kind of electrostatic charge to it, and you narrow in and narrow in and narrow in, you'll eventually get down to that quanta of charge, the single electrons that are making up that charged object. Whereas with a magnet, you can't really narrow in on just the North Pole. That's because magnets are really just made up of more smaller magnets, which we call magnetic domains. And so if you were to take a bar magnet and break it in half, you just have two magnets now. And if you take those pieces and break them in halves, now you've got 4 magnets. And that's because you've got these little things on the inside, which we call magnetic domains. And you can think of them really just as being, you know, small magnets that make up something that's magnetized. If something isn't magnetized, just this random piece of metal right here, you can see that all these little magnetic domains, they're pointing in different random directions. But if you do have something that's magnetized, that's because all these magnetic domains are all pointing in the same direction.
I don't know how magnets work. You know what I'm saying? If you look at pet cats and dogs and all the things we consider miracles, I freak out over some magnets. You know what I mean? That's legit.
All right, back in FET, we've got a little bar magnet here in our compass, and we could move the compass around this bar magnet, and we'd see, depending on its location, it is deflected a different way. It's almost as if the force on this compass depends on where it is sitting around this bar magnet. And so if we were real careful, we could plot what the forces are on this compass at different locations around this bar magnet, and we would end up with this map of vectors that describe the force at any point around this bar magnet. And we already know what something like that is called. That's just a field. In this case, it would be a field describing what magnetic force this compass is experiencing. So we would just call that the magnetic field. And so this is a picture of the magnetic field, and it's going to look similar to things that we've seen in electrostatics, but again, we can't confuse the two. This does look like the dipole situation that we saw before, but this is not really an electric dipole. In fact, this is not an electric dipole at all. This is just the magnetic field around a bar magnet.
That's legit.
And so for many years, this was kind of it with magnets. You just had this oddity of nature where you had some materials that you could just consider to be magnetized. They would have a north pole and a south pole, and you could break them up and just end up with smaller and smaller magnets. And even if we use the ideas of chemistry that we have now with breaking things down to their atomic structures and looking at these intrinsic magnetic moments, it's really just magnets the whole way down. And that was kind of where people thought we were going to get stuck. It wasn't until the early 1800s when people realized that there was something that we could link these magnets to that was another kind of oddity of nature up to that point as well. We can actually link electricity and magnetism very, very closely.
Now! Not this time, Magneto.
So in this setup, I've got this fancy compass thing over here, and I've got a D-cell battery and a wire. And so if I bring the wire underneath the compass and connect it, we can see that the compass actually moves. And once I disconnect, the compass goes back to the way that it was before. But if the wire is above it and we connect, we see the compass moves the other direction. And when I disconnect, it again goes back to the way that it was before this experiment. All right, in this experiment, I've got a loop of wire that's connected to these leads, and these leads go to a digital multimeter that's going to pick up voltage somewhere in the millivolt range. And so watch what happens as this magnet is brought near this loop. As it moves in, there's a pickup of voltage that's on this meter, but leaving it in, there is no voltage at all. It only seems to have an effect when that magnet is moving into or out of that loop. And so this link between electricity and magnetism is how we end up with devices known as electromagnets. And so if you were to look at the magnetic field around a wire, you actually get this circular magnetic field. And the way that we know which direction this circle is moving is based on the right-hand rule. So that's one of the important things about the electromagnet is that moving charges or an electric current, they can produce a magnetic field. So now there's not just standard bar magnets as the only way to create a magnetic field. You can do it with electricity as well. You get an interesting field if you do that, and the way that we know the shape of that field is from our right-hand rule. So in the picture that we have here, we've got current that points downwards, and so the rule for this right-hand rule is that our thumb points in the direction that current is flowing. In this case, our thumb is pointing down, and then the magnetic field is going to curl with our fingers. So our fingers would be the shape of the magnetic field, which if we're looking down from the top of this wire is clockwise. If the current had instead been pointing up the wire, our thumb would go up and our fingers would curl in the opposite direction. So the magnetic field around a current carrying wire is always going to be circular, and the direction, clockwise or counterclockwise, will depend on your right-hand rule, where your thumb is the direction of current and your fingers curl to give you that field. And so then at this point you might be curious, well, if electricity can make some kind of magnetic field, what would be the properties that we could change about that electricity to create either more magnetic force or less magnetic force? And so the formula ends up looking like this. Your magnetic field strength is going to depend on this new constant, which we call mu-naught. It's the permittivity of free space. It's basically how well that magnetic field can go through free space. And it has this value right here, 4 times pi times 10 to the negative 7 Tesla meters per amp. Current is also in the numerator, and then we're going to divide this thing by 2 pi r, where r is technically a radius because it is the distance from the wire out to the magnetic field wherever you're measuring. So if we wanted to measure the magnetic field further away from this wire, then we would just have a larger r. And so this is the formula for magnetic field strength around a current carrying wire. where B is our magnetic field strength that's measured in Tesla, and it really depends on some constants, and then current divided by how far away you are from the wire. As current increases, magnetic field strength will increase, and as R increases, as we get further away from the wire, magnetic field is going to decrease. This is our formula for the magnetic field strength around a current carrying wire. And other than this scary constant out front, it's really not that difficult of a formula, and it only really depends on two things: how much current you have and how far away you are from the wire. More current means more magnetic field strength. More distance means less magnetic field strength. But what if instead of having a straight wire, what if we had a loop of wire? What if we wanted to have a coil of wire? Then what would the magnetic field look like? Well, that device is pretty well known. It's called an electromagnet, or sometimes a solenoid. And so you've got some battery that's connected to a loop of wire that usually goes over some kind of core, which is some kind of metal that sits in the middle there. And if you were to connect this circuit, you're going to get a strong magnet that's created just by this electricity right here. And the way that we can figure out the direction of that magnetic field is again with the right-hand rule, but this time it's different because our thumb would have to follow that loop around each of those windings. So instead we flip those rules. For a solenoid or an electromagnet, instead of a straight current carrying wire, our fingers are going to represent that current, and our thumb will be the direction of the magnetic field. So in this case, with the wire that we have, using conventional current, which comes from the positive side of the battery, our fingers are going to go up behind that piece of metal and loop over, giving us a magnetic field that points in this direction. And so you can use more or less this same formula to figure out that magnetic field strength as well. It's going to depend on how much current you have and how far away you are from the center of that core.
I just guessed that you'd overlook one simple thing. Your magnetic power only works on metal, like all magnets. But my gun isn't real. I made it out of wood, specially to fool you.
What? A wooden gun?
And so that's about it for your electromagnet. There is a way to orient your wire so that you can create a magnetic field. And the main takeaway is just that moving charges or an electric current, they produce a magnetic field. So you can actually use current to produce magnetism. It doesn't have to just be those fancy rocks that happen to come from magnesia. And we can figure out the shape of that magnetic field using our right-hand rule. But that was just one of the experiments that we talked about. It was just the experiment where we could create some kind of movement in the compass based on our electric current. But we had another one as well. There was actually a way to create some kind of voltage based on just moving the magnet around. So it's kind of like the opposite idea of that. It's not just that current produces a magnetic field. We can make a magnetic field produce current as well. And so that's going to be the content of our discussion tomorrow when we cover this idea right here, electromagnetic induction, found by Michael Faraday back in the 1830s. So that's going to be our plan for tomorrow. As always, shoot me an email if you have any questions, and I guess I'll see you later.